just as a quick review of what we've done last time around, we are busy solving linear systems. So if I asked you to perform Gaussian elimination, you would go through a process of eliminating what we call forward elimination. So you pick a pivot element, you start with the first element in the matrix, and kind of use that element to delete all of the coefficients, or delete meaning make them zero, okay? All of the coefficients below, and then you move on in the matrix to the element in the Q2 position, or the second diagonal position, and do the same thing for the elements below, and you keep going. So in this process, I obviously need sort of a nested loop to do that, right? Because I'm walking over or traversing over a matrix. Okay? So once we perform that, we have what we call an upper triangular system, and then we do back substitution. I start from the end, because that's where I have a simple case of coefficient times my, say, x3 is equal to another coefficient, and I can just calculate that and then move it backwards and incorporate information as I have it. So we have done forward elimination. So just to remind you of the code, I have updated and actually uploaded the code, including to what we're going to go through today, just in case you have trouble catching up. So if you look at this Lecture 6 Linear System Part 1 Gaussian Elimination Python notebook, it's uploaded into the code. And there is another Python notebook that is not a notebook, that is just a Python code that I'm going to get to later. So you can download those. But you can also, like, I do want you to work with me. This is just a backup in case you need to catch up. So this is what we've done. Essentially, we went step by step. So first, and this is a way to build the code, you first need to know how to solve things by hand in order to program it, but you want to speed yourself up once you program it, and you want to generalize it so it works for a system of any size. Right? So you solve it on your toy problem, which is 2 by 2, 3 by 3, 4 by 4, something relatively manageable. And then you try to figure out, you kind of eyeball the generalization. You want to have for loops in there that run for the system size, and that system size could be anything. Okay? And that's the objective here. And that's why we practiced all of those abstract summation formulas that you have to write a Python loop for. Okay? Because you come up with a formula of that sort, and you need to know how to program it. So there's mechanics of just like doing it quickly, right? And that's what we practiced basically for our exam 1. And now you're supposed to apply that knowledge to come up with an algorithm that solves a larger system. So we have something that can go along. So basically what we did is last time, we wrote it down. Okay, you write it on a piece of paper. I was writing it as part of the code, so I'm faster in converting it, but basically this is where piece of paper works magic, so that you can think clearly. Okay, it is easier to think while writing than necessarily while typing, and then you just kind of notice the rules that you could actually generalize. So we actually ended up creating a nested loop that does this elimination. So essentially, I figure out my coefficient, okay, for the current row J and element that I'm working with, or the row K and the element like in the column J that I'm working for, and then I just say, okay, replace this kth row with kth row, the original one, minus this coefficient times the one that I'm using to eliminate things with. Okay. And this is my simple rule that I typically do by hand, but it's just within the for loop. It's much more powerful because it can get executed. And do the same thing for B. We have to work with B in parallel. Now, this is a matter of design of the code. I could have created that augmented matrix and just work it all at once. That's an option. I kind of like thinking about B separately, at least in terms of coding. But that's now a matter of choice or style. And then this actually does it's not a big code, right? But the powerful part is that I can go from 0 to, basically M is the size of my system, M by M, or N by N, however you turn it going around. So I can run this for any system size. One caveat that I'm not right now checking, you will get to do that for your homework. You will basically adjust this code to handle also cases when this is 0. This is where my pivot element is 0. I shouldn't be dividing by 0 here. And I should have, I call that the defensive programming, just like defensive driving, okay? In defensive programming, you should immediately evaluate places where you're potentially dividing with 0 or introducing garbage into your code. Because the moment you divide by 0, you're going to get infinity, okay? And then good luck to you with all of the numbers afterwards. So you should actually kind of have checks in code saying, hey, if this is 0, at least print some sort of a statement so we know, so that we're warned. And then deal with it when you encounter it. Right? So think about the code as an iterative way, and it's good to place those checks. But right now, I know it, but I'm avoiding doing it so that we can proceed with the algorithm. Okay? And so then we actually took we checked that this thing works, and then we actually just took that piece of code and created a function that I can execute for any A and B. Okay? But function is more modular code. Also, when I'm evaluating code later, I look at this immediately and I know it does forward elimination, quite literally because the name of the function tells me so. And it's much easier to say that this is forward elimination than this piece of code, right? Plain and simple. Okay? So that's why checks are good. Okay. And we double-checked that. We also double-checked it for a 4x4. I asked you to give me a 4x4. It works. And just to see that we get zeros, so let's execute that once again. So if I shift enter, apparently. Okay, let's now run everything. And let's run my forward elimination, or, oh, yeah, I'm not printing anything. So to check that things are actually working, what I can print is the multiplication, or I'll just print A, because right now I'm just looking at the forward elimination, and I'm wondering whether I made zeros where I'm supposed to make zeros. I have, it looks like. Cool. So now we are going to work on back substitution, and I'm actually going to work on it. So there is a code if you want to download it. I'm just going to actually work from 0 just so that I rewrite. So now I want to form a solution with back substitution, and I will proceed with the same steps in terms of building the code. I'm first going to write the solution. I'm literally using Python as a calculator. Just as I would just to calculate from this situation that is 4x4. And then I'm going to look how to replace that with a piece of code. Okay? How to generalize it and make it more robust. And then I'm going to make a function out of it. Okay? So first things first, if I was solving, so I have A and I have B, right, that I have just defined up there. So basically the way I would proceed it, I would say, minus x, minus 1 times, I'm going to call this x3 the way I would in Python. So x of 0, x of 1, x of 2, x of 3. So minus 1 times x of x3 is equal to b3, right? So the way I get x3 is by dividing actually 7 and minus 1. I just have to give Python what those actually are. So first things first, I'm going to define myself an x. And x will be zeros. I'm just going to reserve memory space for it of the same shape as b. And I'm going to say, x of 3 is b of 3 divided by a of 3. Does everybody agree with me? I'm going to print my matrix, my B as well, just to see it. Okay? And recall that I'm not working with a column here. I'm just working with a 1D vector. And Python thinks about them as rows. Okay, so that is my x of 3. Now, what would happen if I was actually solving this by hand? I would say, haha, 6 times x of 2, right? Plus 9 times x of 3 is equal to b of 2, right? Does everybody see it? So 6 times this corresponding x plus 9 times x3 that I just computed is equal to 5. Is anybody following me? All right. So I'm going to now literally compute this, and I'm going to immediately compute what x of 2 is in that situation. So it's that b of 2 minus, I'm going to put algebra, so I'm going to put things that I know on right-hand side, and that is a of 2, 3 times x of 3. And I'm going to divide by a of 2, 2. Everybody with me? So that's my back substitution. And that's now I have both x of 3 and x of 2. I'm going to now use these two and put them in the equation above to get x of 1. Yes? And based on this matrix, minus 4 times x of 1, minus 8 times x of 2, minus 12 times x of 3 is equal to minus 2. Yes? Okay. So I'm going to immediately rewrite that as just computing my x of 1. And I'm following this model that I have. So it's like my right-hand side, b of 1, minus a of 1, 2 times x of 2 minus a of 1, 3 times x of 3, and I'll divide by a of 1, 1. Forward elimination, yes. For back substitution, I have to have upper triangular matrix. And if I don't, then it doesn't work. That's why I have kind of that last one almost computed, right? The last. And then finally, my first one, now that I have 3 previous ones computed, I can plug them in. So it's this 1 times x of 0 plus 2 times x of 1 plus 3 times x of 2 plus 4 times x of 3 is equal to this first element in B. Yes? So following the similar, when I put what I know on the right-hand side and divide by that for a of 0, 0, I'm going to get that this is b of 0 minus a of 0, 1 times x of 1 minus a of 0, 2 times x of 2 minus a of 0, 3 times x of 3 divided by a of 0, 0. Whoops. Everybody agrees with me? Has anybody spotted an error? I might have typed in a typo. I'm going to double check in a second whether I did things correctly. So I can print my x at the end, but more importantly, I can print a multiplication np mathmo a of x, and when I subtract b, I better get zeros. Ax minus b should be 0, right? If my ax is equal to b. So this is the way to check that you actually got the correct result. So let's see if I had typos in there. Moment of truth. I'm good. So this is just now using Python as a calculator to help me solving my system essentially by hand. Okay? It works only for a 4x4 system. I don't want that. Okay, I want something more general. Does it appear I have a pattern? Yeah, something's kind of regularly growing. Okay? So it does. So let's now actually try to make this more general. And what I'll do is just like before, I'm going to copy this entire thing, and I'm going to do a new cell, and I'm going to try to make things more general right in place. Obviously, I'm going with a for loop. I'm starting, I define my first value, right? And then I should have a for loop over all of the values going from the bottom up, right? So let's generalize that. I want more general, so I'm going to say, hey, m or n, I like n better, is length of my b. So that's going to give me length of 4, right? So then this 3 is actually n by n minus 1. Yeah? Mm-hmm.
Why don't you do the same thing that you did in the last one? Where you did like n comma n equals 8 actually.
This is one-dimensional array, so doesn't matter. Just I'm doing an alternative way. Yeah, you can. Okay, so cool. Now I'm gonna write this as a for loop. So I'm gonna say for, I'm gonna call it I. My I goes from 2, in range. My I goes from 2, 1, 0, right? So my range starts with n minus 2, right? It ends up with 0, which means I have to put a minus 1 here. That annoying little thing about Python and range function. And I'm stepping by minus 1. So that way I'm going from bottom up. Does everybody see? So I'm trying to replace this with a one line, right? So this will execute for every I. Okay? So my x of I, and now I'm looking at the pattern here, is b of I minus something, some sort of a sum. That sum seems to be growing. And right now, for this moment, I'm going to literally write sum, and I'm going to worry about computing it in a second. And I'm dividing by a of what in terms of I? So those were the easy parts. So go with the low-hanging fruit first. Even if this in between something confuses you, I'll write it as some sort of a sum and then come back to it later. So this is a general pattern of what I need to have in my code, right? And now I'm just going to figure out how to write this sum. Okay? So this is a sum that I'm computing, and I'll have to have another loop in there to do that. So what's the first thing that I start when I'm computing sums? Initialize. Write what you know. Takes the edge out of the rest, actually. Okay, now step by step. I will need, so this sum is at my first step, it's only one element because I only have so far one x computed. Then I go one up and then I'll have two elements. And then I have three elements depending how many x's I already have computed, right? As I start from the bottom. So it's something that depends on where I'm at. So there's some for loop involved, and it somehow depends on I. Okay? So well, let's write for loop. So I'm just going to say, hey, for, I'm going to call it j in range. And right now I'm going to leave it open. This sum is starting from the previous sum, and it's always adding, let's do this last element computed. So what is this if my I, okay, is 2? What is this in terms of I? So it's A of I, comma. That's going to be this j that is changing. Okay? ij times x of j. Yeah? And then we'll figure out what j is. So I'm always adding one at a time. Huh. And then it seems that it's always like when I look at x of 1, I will always have one here, right? So this part is always A of I, my current element that I'm working on. Yes? And it's this part that is growing. So what is this j? So in first time, my j is only one of them, and it's only 3. When I have x of 1, I have 3, but I also have 2 because I have computed both. And then I have 3, 2, 1. So it seems that my range is going from where to where? Three, and 3 is my last element. This is the one before. So it's, if this is I, this is I plus 1, right? This is I plus 1. This is actually n minus 1. So it goes from I plus 1 to n minus 1. Does everybody see that? So if this was I is equal to 2, I'm going to just replace right? 3 happens to be the last one, so that's my n minus 1. Okay? Then if my I is 1, I have I have 2 and 3. So for I, j is 2 and 3. For I is equal to 2, j is 3. And for my last thing, when my I is 0, I, 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 I. So again, you can do this on paper. I'm doing it within a code. My j is 1, 2, 3. Do you see? 1, 2, 3. So how do I program this pattern that my j's depend on I? I'm always going up to 3, or actually starting from 3. And I go down to essentially I plus 1. So 3 is also I plus 1. Yes? 3 down to I plus 1. 3 down to I plus 1. Because at step I, it's all of the larger elements than I, larger in terms of index, that have been computed already. And I'm using what has been computed already. So at this step I, which is for 2, the only one that has been computed already is x3. At step I is equal to 1, 2 that have been computed already are x2 and x3. Okay? At step 0, 3 that have been computed already are 1, 2, and 3. Yes? So I have to somehow formalize that so that my j is kind of growing regardless of the situation I have, whether I have 4 elements, 5 elements, 6 elements, or so forth. So this is indeed to go however many I have. It's actually more, it's 1, 2, 3, or 3, 2, 1, however you want to see. So this is going to go to I plus 1, but because of the range, I have to put I. An alternative is just to put I plus 1. Is this easier to look at? Yes?
Why is n minus 1 the same as I plus 1? Or why did you replace this?
Either way it works.
How is it?
It's just, am I going this way or this way? Right? So look at here. Let's go back to this system by hand. Okay? I'm going over those x's that I have computed already. So for 2, I have computed x3 only. Okay? And for 1, I have computed 2 and 3. Okay? So whether I add this sum by starting from 3 and then go down to 2 is the same as going from 2 to 3. Okay? And when I evaluate this range n minus 1, comma I, comma minus 1, in terms of the elements that it has, is the same as range starting from I plus 1 to n not being included, because range function works that way. Remember that part we don't like about range function.
So why would it be I plus 2? Do you want to include I plus 1? Then why don't you have to add another one? Because you're going down in I?
Yeah, so your starting point is always what it is, what's written.
Uh-huh.
And that ending point,
You're getting smaller.
yeah.
Okay.
Ending point, you're not supposed to hit it, you're supposed to give it. And again, I don't like that about range function, but I'm not the one who implemented it. Does everybody see this? Questions? There's like awful silence in class. So let me now remove this part. This was just a helper, and see whether I did it right. Okay. Looks like it for a 4x4. So now you take 2 minutes and create a function out of this. I want to call it back substitution. So I would just copy the whole thing into a new cell and just create a function out of it without any printing or anything, just this portion. So your A and B are inputs and X is an output. So strategy for code development, again, is start from an example that you know and that you can easily check the solution for. Use Python as sort of a glorified calculator to calculate things just by hand, so to speak, one by one. And then see how you can generalize this for a system that is larger than your 3x3 or 4x4 toy systems you started with. And try to just, like, if you're confused by something, you don't know what this range should be over, just write it as range and fill it in later. If you were in the exam kind of situation, you would get points, right? Oh, you didn't do the range correctly, but you got the other logic correctly, right? So try to see what you know and just write that down and then improve step by step. Don't focus on attempting to write the code all at once. Ain't gonna happen for anybody. It's going to happen for me if I'm just like, I've been repeating this code all over again. So yes, I can come out and just write it, right? But even then, I'll have some typos and whatnot. So you always have to be on the lookout for little issues. Yes? Question?
There's just one. I'm just like wondering. This is like the only. Are we gonna have to drive this or something? Because this is the only. I mean, I don't understand the point. This is like, I don't know, is this already gonna have to derive or something?
So I could give you a problem where I ask you to derive, to create an algorithm that does things in a generalized situation. One simple example is that there is a tri-diagonal system. We have an example of how do I type that in, or whatever, to create a tri-diagonal matrix out of it. I would say now, create a modified algorithm that just works with a tri-diagonal system. That was actually an exam question at some point. That is not just repeating this, because this is an overkill. So I'm going through the steps of how am I building an algorithm. Okay. Because you will be in a situation that you have to build it on your own. So you have to see this, know the solution by hand, write it down, see a more general way to do it so you can repeat it, right? And then
Explain why the range for I is
this one. So I have already done first one.
okay.
Now technically, actually, it works even if I start from -1 and I don't include this line. It does work. This will be an empty sum, and that's fine. So you can actually verify it. So I mentally wanted to start from something, but yes, actually the code works if I remove this line and I just start from n-1 here. Normally you have to have a starting point of some sort, and I just explicitly wrote down that starting point, then I don't need to recompute it essentially. Because n-1 for n by n system, this is where your last element is stored. Because it starts from 0, so it's 0, 1 through n-1. This sum, basically for this case, doesn't exist because I don't have computed values already. So it's really just b of I divided by a of ii. And sum is just a 0. Okay? For this first one. And it works. So the code actually works if you just start here from n minus 1, and you don't need, then you don't need this line. Okay. There's multiple ways. You can always have a starting point to begin with and then create a loop, right? Or you can try to encapsulate everything within the loop. But some initialization is needed. So here we did have to initialize x just to give it space, right? Okay. So now I hope your function, back substitution, works like something like this. So I basically just indented the code. Inputs are A and B. And I return my x at the end. Okay? And the way I call this is say x equals to, so now my Gaussian elimination is Gaussian elimination of A and B. A, B, I do forward elimination, and I return x from back substitution, and I return x. That is my Gaussian elimination function. So finally, if you don't want to type it in, again, I posted the code. So let's now go and do this example that I had at the beginning. I'm going to copy. And let's test. This is my example. So I'm going to say, hey, x is Gaussian elimination of AB. And I'm going to print my A times, not A times x, np matmul of A comma x minus B as a test. Moment of truth. Whoops. Elimination. Did I type things correctly? Ah, I did not execute this cell. And if you don't know how to spell elimination, make sure there we go. One more thing. So now I actually want to push this code and see how good it is, how fast it is, and all that. I'm not going to do that in a notebook because I actually want you to later test and see what is one of the larger systems you can solve on your computer. So to be a little more stable and avoid web browsers locking up, we will go to Spider. And I have already posted Lecture6 timing. This is just py code, just the Python code that I want you to download now and open Spider. So now I'm going to basically take the functions that I have just defined. My forward elimination, I literally copied them. So import NumPy, forward elimination, back substitution, Gaussian elimination. And now I'm going to time the code and see how long does it take to perform versus whatever it is that Python does with its solve function. So I'm going to start with 1,000, n is 1,000. There's a timing. So I'm importing a module that does the timing. And all I'm doing here is I'm creating myself a random system. It doesn't matter what the system is. I just want to see how fast is my code. Okay? So A is just a random matrix that is n by n, and I'm defining n as 1,000. Just give me 1 minute. B is just a random vector of n elements, and I'm start the timer I do Gaussian elimination, which is the code that I have just developed, and I do end of the timer, and then I just put end minus start is the time that has elapsed. Okay? And I repeat the same for the solve, NP solve. Let me quickly execute it for you. So if I do this, so my Gaussian elimination takes about 4 seconds, and whatever solve does takes 0.05. Obviously, we're not optimal here. We have some issues. We don't know what algorithm is in there right now. Okay? Doesn't matter. But I don't want you, and I don't want you to push your computers. You know, mileage varies. You will get slightly different time because you have a different hardware. Okay? And the question is, how far can you go? Can you go 1,000, 2,000, 5,000? At 10,000, things might start breaking down, which is why I don't want you to use notebooks, because there's an additional software layer that we don't need. Okay? So we're going to actually compare the timings from this group. Okay? Because we want to, in reservoir simulation, we want million by million. So just to see whether we can achieve that on our little laptop. It's going to be this code is all posted. Right. So just use this stuff, just to eliminate the web browser. Because that can walk out. I don't want 20 browsers. What you will have to turn in this time, just execute. So, but not now. I'm going to pause for the time. So, for Friday. Yes. So, I'm going to create an assignment for Friday. Nobody's listening to me.